If light can be a wave or particle, what about matter? In 1923, it was proposed by de Broglie that matter might have wave properties as well as particle properties. The wavelength of a particle can be calculated using the de Broglie relation. Wavelength is equal to Planck's constant divided by mass and velocity. For a baseball of ordinary speed, the equation gives us a very small, unobservable value for wavelength. However, for an electron, the calculated wavelength is large enough to be observed. So how do we observe this wavelength? We must think of an experiment that demonstrates a phenomenon known to be a property of waves, and that is diffraction. After several years of trying, in an experiment completed in 1927, electrons were shown to diffract, exhibiting wave-like behavior. This showed that matter can be described as a wave and that matter has wave-particle duality. This discovery contributed to the development of quantum theory, which makes predictions by using the wave nature of matter. One other important discovery that contributed to quantum mechanics was the Heisenberg uncertainty principle. Heisenberg showed that there is a limit to the precision with which we can measure complementary properties. For a particle, it is impossible to simultaneously measure its position and velocity. In other terms, if you know one, then you cannot know the other. The uncertainty principle states that the product of uncertainty in position and the uncertainty in velocity must be greater than or equal to h, Planck's constant, over 4 pi. This is a very small number. For life-size objects whose masses are large, uncertainty in position and uncertainty in velocity both can be very small and not break this inequality, meaning that you can measure position and velocity with certainty. If you know position and velocity, then you can define a path for the object like the path of a tennis ball. However, subatomic particles are bound by uncertainty. Particles such as electrons have very small masses, and if either their position or velocity is known with certainty, then the uncertainty in the other property must be large. This means if you know where the particle is, you cannot know its velocity. Or if you know its velocity, you cannot know its position. As a result, you cannot determine a definite path for an electron, and the position of the electron is fuzzy. The electron can be found anywhere in that fuzz. However, we can calculate the probability of finding the electron at a point, at a location. This calculation allows us to predict the most likely spaces to find the electron. This is how we are going to describe atomic orbitals. In the soccer game analogy, the object of interest is the ball and its future. To predict its future path, we must know both its position and velocity. However, from the still image, we can only get information about the position of the ball. The direction and speed of the ball is uncertain. Consequently, we cannot determine the ball's path, whether it's going to be a goal or not, with 100% precision. However, we can talk about the probability of the future of the ball. The ball's future, a goal or not, is probabilistic, just like the future of subatomic particles. The probabilistic nature of subatomic particles is described by quantum physics. Particles are described by their wave functions, which define their wave behavior. Wave function is denoted by the Greek letter psi. What is important for us is the probability, which is found by squaring the wave function psi squared. This is the probability of finding the electron at a given point around the nucleus. The wave function is solved by the Schrödinger equation. The solution to the Schrödinger equation are the quantum numbers, which describe orbitals, which are regions of high probability of finding an electron. Orbitals are defined by their size, shape, and orientation. For example, an orbital is shown here by a region of blue shade. That means it is more likely to find the electron within that blue shade. The general shape of this orbital is a dumbbell shape, and it is oriented along the z-axis. The solutions to the wave function, the principal quantum number describes size. The second quantum number distinguishes orbitals. The third quantum number is the magnetic quantum number, m sub L. Let's summarize what we have learned about quantum numbers in a concise table. We first saw that value of n can go from 1, 2, 3, 4, up to 7. The value of L depends on the value of n, such that L goes from 0 to n minus 1. So if n is equal to 1, L can have only one value of 0. This doesn't mean that there is no L. It means there is one value for L, value of 0, which means that there is only one kind of orbital determined by its or defined by its shape in n equals to 1. Let's move on to n equals to 2. If n is equal to 2, then L can be 0 or 1. If n is equal to 3, L can be 0, 1, or 2. If n is equal to 4, then 0, 1, 2, 3 are the possible values for L. And remember the letter notations for the values of L. 0 corresponds to S. All zeros actually are S. Types of subshell. This is the type of subshell. Remember, L tells you the shape. So S or L equals to 0 corresponds to a shape, specific shape. We gave number 1 the designation P, and number 2 was D, and number 3 was F. As you can see, each shell has everything that the previous shell has plus one more. The number of subshells, L, increases by 1. At this point, we can now move on to the value of m sub L. This depends on L, that it goes from negative L, increasing by 1, to plus L. So for the value of 0, m sub L can only be 0. It doesn't mean there's none. There's only one value. That means there's one orbital. M sub L, the different values of m sub L tell you the different orbitals, the different number of orbitals. How about for L equals to 1? The number of m sub L, the values can be negative 1, 0, positive 1. There are 3 values. It means that there are 3 p orbitals. these three values mean that there are three orbitals of the p kind. This one value here means that there is one orbital of the s kind. We can do the same continuously. 0 for the s, -1, 0 plus 1 for the p, -2, -1, 0 plus 1 plus 2 for the d, and which corresponds to, we count 5 numbers, right? 1, 2, 3, 4, 5. That means there are 5 d orbitals with different orientations in the third shell. The SPD configurations for the fourth shell are the same. They're going to be exactly the same as the third one, but they're going to have an additional one because there's an F type of orbital in the fourth shell with m sub l values -3, -2, -1, 0, 1, 2, and 3. How many values do you count here? 7. That means there are 7 f orbitals in the fourth shell. So when you want to write the total number of orbitals, the spaces for electrons, in the first shell there is one orbital, and that is the 1s orbital. In the second shell there are total of 2 different types of orbitals, s and p orbitals. There is one 2s orbital and 3 2p orbitals. In the third shell, there is one 3s orbital, 3 3p orbitals, and 5 3d orbitals. In the fourth shell, we have one 4s orbital, 3 4p orbitals, 5 of the 4d type of orbitals, and 7 4f type of orbitals. And we can take this one step further to write down the maximum electrons each orbital can take. And there's a rule here, 2 per max of electrons. That means each orbital can take 2 electrons maximum. So one orbital of 1s type can take 2 electrons. One orbital of the 2s type can take 2. 3 orbitals of the 2p can take a total of 6, because 3 times 2 is 6. Total of 8. When it comes to the third shell, one 3s orbital can take 2 electrons. 3 3p orbitals can take 6 electrons, and 5 3d electrons can take a total of 10 electrons. I'm getting these numbers by multiplying the number of orbitals by 2. And the same goes for the fourth shell, 2, 6, 10, and 14. And these are the maximum number of electrons that can be put into those shells.